This is Lab 4, Circuits. The purpose of this lab is to predict the behavior of circuits with resistors in series and parallel, measure the actual voltage and potential difference, and examine the behavior of ohmic resistors, non-ohmic resistors, and capacitors. The most important physics concept used in this lab are the loop rule and the node rule. The loop rule states that the overall potential difference for a complete loop is equal to 0. This is from the natural log of delta V over delta V naught equal to negative T over RC. The node rule states that the overall current going into a point will equal the overall current going out of that point. In the change conversion, energy conversion in series part of the lab, I used the loop rule and the given resistance values to predict that the currents 1 and 2 were equal to 0.02 amps. I was calculating that with the formula listed on the screen. Using the circuit construction kit, I created my circuit and learned that my predictions were correct. And when I reversed one of the ammeters, the readings were the same for the currents. When the top ammeter was replaced with a voltmeter, the voltmeter read negative 3 volts and the remaining ammeter read 0 amps. The voltmeter readings of potential difference at various points around the circuit were calculated, and these values summed to 0. AB was 3, BC 0, CD is negative 0.96, DE 0, EF is negative 2.04, FG was 0, GH was 0, and HA was 0, as well as the current was equivalent to 0.02 amps. Here on the screen, I show the circuit where you can see what potential differences were calculated, and the graph here depicts those, and as you can tell, that matches the values that I calculated. When the voltmeter was attached, when the voltmeter was attached, the ammeter reading should not have changed because the voltmeter acted as a perfect resistor with 0 resistance. But since the ammeter is not actually a perfect resistor, when a second ammeter was added in parallel, it decreased the original reading of the ammeter due to an increase in resistance. When I calculated the resistance of parts of the circuit using my measurements, the calculated values were close to the given values for resistance. For the resistance of 47 ohms, I calculated 47.95 ohms. Of 100 ohms, it was 102.5 ohms. The wire resistance was 0 ohms, and the ammeter resistance was also 0 ohms. For the RC circuit part of the lab, charging the current flows into the capacitor and discharging the current flows out of the capacitor, and as a result, the light bulb glows bright then dim. The light bulb goes out when the capacitor reaches peak charge or empties of the charge completely. This is due to the flow of the current stopping after charging or when discharging occurs. For the time-dependent voltage across the discharging capacitor section of the lab, I measured the potential difference as a capacitor charged and then took the ratio against the initial voltage. The formulas are on the screen, and you can see how the natural log formula was derived from the original equations in the first dot. I plotted the natural log of the absolute value versus time, and that's shown on the next slide. I then compared my calculated value of 1 over RC, which is the slope of the graph, to the value of 1 over RC for the circuit. So as we can see, here's the graph of the ln of delta V over delta V naught compared with time. And from 1 to 7 seconds, the 1 over RC value is 1 over 5, which was close to the circuit value of 1 over 6. But when you look at 1 to 20 seconds, the computed value was 1 over 13. And the significant decrease in the value could be due to the change in potential difference that decreases as time increases. The additional questions in this lab are: what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated one? What's different about a real one, and how would it affect the circuits we hooked up? Well, a real ammeter is not perfect, so therefore it does not have a resistance of 0, and it would have added additional resistance. The next question is: what if you were using this lab in real life and used a real battery instead of to charge the real capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge? Would the prediction happen in real life? So the model predicted that the capacitor would fully charge instantaneously, essentially, but in real life, the wires and batteries that are used are not perfect and would add resistance to the circuit, thus increasing the time to fully charge the capacitor. Thanks.